Hey everyone, this is Paul, and in this video I'm going to be explaining why infinity isn't a number. Now last time we defined a number as an element of an ordered field, so check out that video for a definition of what an ordered field is and what we mean by numbers. So here are sets as before, with the rationals and reals both being examples of ordered fields, and the integers and natural numbers being subsets of the reals. Now the really important one we're going to be talking about here is the set of real numbers, in part because the rationals are contained within it and are actually dense within it, and because any complete ordered field is isomorphic to the real numbers. Now I'm not going to be proving this point, but if you're interested, I can provide some information on this. And what we're going to do is kind of a proof by contradiction. We're going to suppose that infinity is a real number, and we're going to end up with serious issues to show why it can't be in there. So let's begin. Let's suppose that infinity is a real number. One of the properties of infinity, because it's a upper bound of the set, is x times infinity is equal to infinity for any x greater than 0. Now let's just choose any x, doesn't really matter, we'll just choose 2, and we get 2 times infinity is infinity. And what we do is we invoke field axiom M5 of multiplication to show that we must have multiplicative inverses that give us 1, and we simply divide by infinity on both sides, and we get 2 times 1 equals 1, or 2 equals 1. And this is really not good because it ends up violating our ordering that we had on the set, and you can let x be something else, let x equals 3, you get the same result. It actually works for any number. What we do by letting infinity into our set is we destroy the assumed ordering we had. And this contradiction comes from the fact that the order that we have states that one and only one of these statements is true. X is either strictly less than y, x is equal to y, or x is strictly greater than y. And you can turn this into a nice little argument using our definition of numbers as elements of an ordered field by saying, look, premise 1, if infinity is a number, then 1 equals 2. Premise 2, obviously 1 does not equal 2, and therefore infinity is not a number. Premise 2 being logically equivalent to it is false that 1 equals 2. So this is why infinity isn't allowed. It violates the ordering of numbers and leads to all sorts of other contradictions as well. And this is why analysts like Walter Rudin, whose work perhaps makes him the most famous analyst of the past century, are very careful to define infinity as a symbol. So here's work from baby Rudin. He defines the extended real number system as the field R with two symbols, plus and minus infinity, so not even defining them as numbers, but as symbols, and saying, look, the extended real number system does not form a field, but it's customary to make the following conventions, and when desired, to make a distinction between real numbers on one hand and symbols on the other, with the implication being that infinity is not a number. Likewise, David Hilbert says, look, the infinite is nowhere to be found in reality. It neither exists in nature nor provides a legitimate basis for rational thought. The role that remains for the infinite to play is solely that of an idea. And this is why analysts, at least in standard analysis, tend to use infinity as a limit, things going towards infinity, rather than treating infinity as a number in and of itself. Now, you may say perhaps infinity isn't a number, but maybe it can still be reached by addition or by infinite addition. Well, this isn't going to work either. And you can make this into a little argument itself. Look, premise 1, if infinity is in the real numbers, then infinity cannot be reached by addition. And the reason for this is field axiom A1, which states that numbers are closed that are in fields by addition. This is additive closure. Then premise 2, infinity is not in the real numbers. Once again, as we saw previously, otherwise 1 would equal 2, which would contradict the ordering of the real numbers. And the conclusion is, therefore, infinity cannot be reached by addition. And the key implication of this is you can't count to infinity by successive addition. And as a result, it's odd that both Alex Malpass and Wes Morrison are going to accuse William Lane Craig and others of begging the question, when I would argue it's their published work that clearly does. To assume you have infinite time is to move yourself out of the field axioms, to basically bring yourself to a case where you can add to infinity, which is obviously ridiculous. So when Wes Morrison claims, look, if you ask how many distinct future events will there be, the only sensible answer is infinitely many, we can simply cite additive closure, field axiom A1, to show why he's begging the question. Once again, elements of an ordered field or elements of a field in general are closed under addition, and this just has to do, even if the set has an infinite cardinality, this is just true, period. Put another way, it's logically impossible to get a number larger than a finite number from successive addition, and this is because of additive closure. In this case, invoking infinity, I think, ends up hurting you. If you claim you have infinite time to do successive addition, you end up either having to claim that set theory itself breaks at infinity, or that logical contradictions are somehow metaphysically possible at infinity. And I'm assuming Alex Malpass and Wes Morrison would find both of these options pretty unsatisfactory. But once again, this is just kind of the results. Now, let's go over a few objections. I think some of these are interesting and some of these are actually better than others to talk and hopefully get a better picture of infinity. The first one is, why not make a special exception for infinity? When we look at field axiom for multiplication M5, we make a special exception for 0 where we don't have a reciprocal for 0, so why not do the same for infinity? Now, I actually think this is perhaps the most compelling of the different views and objections we have. The problem here isn't that it's M5 that causes the problem. It's the ordering of numbers that break when infinity is introduced in them. And I think this ends up being ad hoc because infinity by definition has the very property that would lead it to this result. So what you're doing is bending the rules for this extra thing. And the question is, why allow this extra thing in there and then bend the rules when the thing by definition has this property that would lead it to cause all these problems? I think the issue comes from infinity itself, not from field axiom M5. And we'll talk about division by 0 here in a second. The other thing is we make an exception for 0 because it's required for field axioms A4 and A5 for having an additive identity. Any number plus 0 needs to be itself, and for having sort of additive inverses as well. If we didn't need to have it, I don't think we'd put 0 in there. And the reason for this is 0 is actually a very weird number. And the reason for this is because it represents something different than everything else. All other numbers represent something or some form of somethingness, like a length or a value or a number of apples. But 0 is a something which refers to nothing or kind of nothingness itself. And 0 is in there because it makes sense to represent addition or multiplication of nothing. But an object of this way is kind of a weird thing and obviously very different than any other sorts of numbers. So when we talk about why we don't allow division by 0, yeah, there's mathematical reasons for it, but I think you can also look at this in terms of philosophical reasons as well. Let's look at infinity and look at division by 0. So here's an intuition for why division by 0 is undefined. If I have a pizza and I cut it into 8 slices, it makes sense to ask how big each slice is. If I know how big the pizza is and I cut it into 8 slices, I can ask, okay, how big is each slice going to be? One way to interpret division is that it tells us how large would each piece of this initial thing be if I cut it into n equally sliced pieces, with n being the number of pieces you're slicing it up with, and they all have to be the same size. But division by 0 is kind of like saying, how large would each piece be if I cut the piece into no pieces? Not some piece that represents some value, but into actual no pieces or nothing. This doesn't really make any sense. You can't get a nothing from something. And this is why analysts are going to define the opposite nature of tending towards infinity and tending towards 0 in terms of limits. It's worth pointing out, once again, I can't make this clear enough, that infinity is not the opposite of 0. Since 0 is nothingness, the reciprocal of nothingness is something or kind of anything, not necessarily something which never ends, which is why division by 0 is undefined. Once again, the opposite of nothing is anything, not something in particular. Now, it's true that infinity and 0 are in opposite directions, and in terms of limits, they tend towards different values. But they're not actually reciprocals because the opposite of a number going towards infinity is still a number, still a quantity, just a number that's going towards 0. Now, when we go to non-standard analysis, this may be actually kind of helpful. The opposite of infinity is something called a hyperreal number, which is an infinitesimal quantity, not a 0 quantity. A hyperreal number is basically a quantity that refers to some non-zero quantity smaller than any real number, just as infinity refers to a quantity larger than any real number. So the way infinity is defined in non-standard analysis, it actually gets constrained by axioms so that the set of hyperreals is still considered to be an ordered field. But non-standard analysis, it's a little controversial because it does kind of lead results that violate the Archimedean principle. So with that being said, I encourage people to take a skeptical but open-minded approach to non-standard analysis. I mean, some people are too dismissive of it and other people are perhaps too accepting of it. Still, when it comes to standard analysis, what we're talking about here, we have numbers that go towards infinity and numbers that go towards 0, which are treated as limits and tend to be rigorously defined in this sort of epsilon delta formation. Now, another objection could be, look, infinity is still a number, it's just not in a field. And at this point, I would just say, look, we're equivocating the word number. In my view, for a number to be able to count and measure, it must obey certain rules about well ordering and other properties. And it also needs to play nice with other numbers in this case. And in our case, if we introduce infinity into a field and want to do operations on it, we end up destroying all the other numbers and the ordering that we assumed that they had. So this is why I would say, look, there are reasons to be skeptical of infinity existing because it causes all sorts of contradictions with the basic axioms of arithmetic. For a number to be a number, it must be able to count and measure and thus exist within an ordered field. Third objection being infinity exists because of the ZFC axioms. Okay, this actually makes a really good point. Axiom 7 of Zermelo-Fraenkel set theory assumes that infinite sets exist. But this is an assumption that cannot be proven if the other axioms are consistent. This comes from Gödel's second incompleteness theorem. Now, this axiom comes from the von Neumann construction of the natural numbers, which I would argue kind of begs the question in favor of infinite sets existing by assuming that this inductive construction of natural numbers is closed. And all the infinity axiom does in ZFC theory, with C being sort of axiom of choice, is just basically assume all the numbers that could ever be counted could be conceptualized or thought of as existing in a set. So I would say this is a good and interesting observation, but it doesn't work to show infinity exists, in part because, once again, it could be seen as question begging by assuming that infinite sets exist, but also just realizing that this is just part of the way mathematics is conceptualized. It doesn't really show that infinity exists as a number per se. And lastly, we get to the last objection, which is, why should I care? Yeah, that's a good question. Anyway, thanks for watching, and I'll see you in the next video.